Hello friends, in this tutorial we are going to learn about AVL trees. AVL tree is also a binary search tree. That is, it follows the same rules as binary search tree follows. That is, left subtree must be less than the root node and right subtree must be greater than the root node. But in AVL trees, each and every node must be balanced. How we balance it? We have a balance factor formula. That is, height of left subtree minus height of right subtree. And AVL tree's balance factor is -1, 0 or 1. If we have this -1, 0, 1, then it is fine. If we don't have this, then we have few rules to make it -1, 0 and 1. So let's consider an example: 25, 36, 41, 52. How we do this balance factor for this tree? It doesn't have left child, right child, so 0. It doesn't have left child, but it have right child. Here have height of left subtree minus right subtree. So 0 minus 1, so it is -1. It is balanced. And here it is 0 minus 2, so it is -2. Here 0 minus 3, so it is -3. Problem we are getting here at the -2. 0 minus 1 are fine. Here we are getting -2. Here the problem is arising. So we have few rules with which we can make it as -1, 1 or 0. So first thing is, if we have imbalance in the right subtree and if they are of the same sign, here it is minus, here it is minus, then what we do is we go for single rotation. That is rotating the tree to the left position. Rotating tree to the left position, this side we are rotating the tree. And if we have the right subtree, example 36, 30, 14, 12. Here it is 0, this is 1, this is 2, this is 3. Because it's left subtree minus right subtree, so it will be positive. So here there is no problem, here there is no problem, but here problem is arising. So what we do, here there is an imbalance. So we turn the descendant, or we turn the tree one position to right. So how we do this? This here problem is arising. So what we do? It's ascendant, nothing but its ancestor, to be turned to the left side. So now the tree look like this: 41, 52. Tree is turned one position to left. So now this is 0. This is 0 minus 1 is -1. This is 1 minus 2. Here we have -1. Here 0. Now it is balanced. So in this way, how we do this for 30, one position to right, 30, 36, 14, 12. This is 0, this is 0, this is 1, and this is 2 minus 1, 1. So it is balanced. Here we have same signs, that is minus minus, here plus plus. What if we have different signs, that is minus and plus? How we do this? Let's take an example for it. Now we have 40, 36, 30, 42, 50, 48. So now we need to consider this tree. Now height of this is 0, height of this is 0. and here left child is 1, right child is 1, so 1 minus 1 will be 0 here. Here 0 minus 2 will be minus 2. Here 2 minus 3 is minus 1. Here it is 0. Here 1 minus 0 is 1. This side okay, but this side problem is arising over here. So what we do? This is minus and this is plus of different sign. Here we have seen same sign, but here we have different sign. So what we do is, this descendant, this is ancestor, this is main part, so this is ancestor, this is descendant to it. Let's do it. So this descendant child will be turned to right side. Like this. 40, 36, 30, 42, 48, 50, 55. It is turned to right like this. So now 0. This is minus 1, this is minus 2, this is minus 3. This is minus 2. This 2 minus 4 minus 2. This is 0, this is 1. So we here when we have different sign, we should do double rotation. If we have same sign, we do only single rotation, either left or right, according to that. But here what we did, descendant left is turned to right, and this ancestor is turned to left side. How? Like this. 36, 30, 48, 42 will be coming here. Ancestor is turned to left side. So now it is 0, it is minus 1, and this is 1 minus 2 is minus 1. Here 2 minus 3 is minus 1, 0, 1. So it is balanced. So in this way, when we have different signs, we turn like this. If imbalance is in the left subtree, now we have here imbalance in the right subtree. But what if we have imbalance in the right subtree, and if they are of different signs, then we go for double rotation. We have different signs. What we do? This descendant right, here we took left side, right? Here if it is on left side like this, this right will be turned to left, and this ancestor will be coming to the right. As we did in this, we do opposite to this. In this way, AVL trees can be constructed. And what if you want to delete a node from the AVL trees? There we have seen how to balance the AVL trees. Now here we will see on deleting the node how it can be balanced. Deletion. Now we have for example 36, 32, 44. Now if you want to remove 44, as it is a leaf node, we can remove it easily. It doesn't affect any balance factor. This is fine. This is first one. Now let's come to second one. 36, 32, 44, 43, 45. It have left and right children. If you want to remove this 44, how we need to do? Deletion follows almost same like binary search tree. So if you want to delete 44, and from 45 and 43, 44 is greater. So 45 will be coming as a root to this. So 36, 32, 45 here and 43 here. In this way we delete, and we need to check for the balance of it, and deletion is done. Now insertion. How do we insert an element in a binary search tree? Let's consider a tree. It's 38, 35, 33, 36, 42, 39, 45. This is 0, 0, this is 0, this is again 0, 0, 0, this is also 0. All are 0, it is balanced. Now we need to insert element 46. Element 46 is greater than 38, greater than 42, greater than 45. So it will be coming over here. So when inserting like this, what we get? This is 0 and this is 0 minus 1, so it is minus 1. And here this is 0 anyways. Now 1 minus 2 is, this is also minus 1. This is 2 minus 3 is, this is minus 1, 0. This is same. In this way, balance, it is already balanced. If it is not balanced, we follow the same thing how we did before. If it is of same sign or if it is of different sign. In this way, insertion, deletion and balancing is done in the AVL trees. So in our next tutorial, we will learn about B trees. So if you like this video, please do like, subscribe, comment, share and click on the bell icon so that you will get to know about the new notifications of the videos which we upload. Thank you.